Okay, the last thing that I want to talk about in the algebra review portions of this course is handling rational expressions, rational equations, simplifying things that are generally rational. At times in calculus, you'll see that in a few weeks, we'll produce somewhat complicated rational expressions through one of our calculus techniques, and we'll likely need to be able to find the zeros, potentially find the domain, possibly find where it's positive and negative. And so we have to remind ourselves a few things. What part of a fraction or rational expression controls whether or not the function is zero? Remember, that's the numerator, because 0 divided by anything else is 0. Now, what part determines where our domain restrictions are? Is where our denominator is 0. So we're just going to start with a pretty simple clean up rational expressions. I'm going to leave number 2 for you guys, and we'll just talk through number 1. Simplify the following rational expressions and find all zeros. So we've got x squared plus 4 times 2 minus 8x squared times x squared plus 4 over x squared plus 4 to the 4th. Now, one thing that people generally are averse to doing is simplifying. People will be tempted to multiply these out, combine terms, but what we should be able to recognize is that each one of our terms has an x squared plus 4. Yes, the denominator has more than the rest, but there's at least some quantity of x squared plus 4s that we can remove. The fewest amount that we see is 1 in both of the terms in the numerator, which means I can remove 1 x squared plus 4 from each of these terms. That will cancel out both of the numerator x squared plus 4s, but there are 4 of them in the denominator, so we'll only reduce to 3. What that will leave us with is 2 minus 8x squared over x squared plus 4 to the 3rd power. Now, unless there's an x squared plus 4 now in our combination in the numerator, there should be nothing else that we can cancel. But it also wants us to find the zeros. So again, if it wants the zeros, we will take the numerator and set it equal to 0. And we will solve for x from there. So we add 8x squared to the other side. I mean, you could keep the x squareds on the left, but I'm going to move it over here. Because there are no x terms, this is not going to require factoring. I'm going to divide by 8. 2 8ths reduces to 1/4. And then we can take the square root, and the square root of 1/4 is 1/2. However, because we introduced the square root and there is a variable involved, it will be plus or minus 1/2 equals x. So this tells us our two zeros in this case are positive 1/2 and negative 1/2. I'll let you practice doing this again on problem number 2, but there are going to be situations where we really need to find the zeros, and it's going to require us to clean up these equations. Now, on the last page of this notes, I'm going to ask you to do that and quite a bit more. So I want you to find the zeros, the values for which the following rational functions are undefined, and then find the intervals over the domain over which the function is positive and over which the function is negative, and we'll use that same sign chart that we used on the inequalities earlier in this lesson. So I've started you with number 1 fully factored, but very often, like in number 2, you are going to have to use your factoring techniques to factor it yourself. Okay, so we've got x plus 4 times x minus 1 times x plus 2 over x plus 4 times x plus 1. So where is the rational function undefined or potentially indeterminate? That will be any time the denominator is 0. While not every single denominator being 0 produces an asymptote, for example, because x plus 4 over x plus 4 is present, x plus 4s, these will cancel and create a hole at the x value of negative 4, but you can remove them. So you have x minus 1 times x plus 2 over x plus 1. But as a note, at negative 4, it's not defined, even though it's not an asymptote. So that's potentially a value where it's undefined. The other place where it is not defined is when our denominator is 0. So when is x plus 1, 0? When x equals negative 1. So that gives us potential critical values for our positives and negatives. Remember, where the function is undefined, it could potentially change signs, not necessarily at a whole in the same way that it does at an asymptote, but we'll keep track of the asymptotes and the zeros to make our little sign chart. So the other places where you can change the sign of a rational is where the numerator is 0, so it's finding the zeros of the remaining factors in the numerator. So the intercepts x minus 1 equals 0 and x plus 2 equals 0. So this is when x is 1 and x is negative 2 respectively. So any potential asymptotes or zeros would need to go in our sign chart to determine whether we are positive or negative. That's 3 of them. So we've got negative 2, negative 1, and 1. Gotta pick nice numbers to plug in. The bad news for us is there's not really a nice number to plug in between negative 2 and negative 1, but we've got negative 3, for example, to the left. We'll call it negative 3 halves or negative 1.5 if you prefer conceptually decimals. Between negative 1 and 1, we can have 0, and above 1, 2 would probably be the easiest. And I'm gonna plug it in sign-wise into what remains. The reason I don't need to plug it into the original before the hole was removed is because regardless of what number you plug in, as long as it's not negative 4, it will be the same sign for both of these. Let's take plugging in 5. 5 plus 4 is positive. 5 plus 4 is positive. Positive divided by positive, still positive. But if you take, say, negative 10, negative 10 plus 4 is negative, but negative 10 plus 4 is also negative. In fact, it's the same negative, and negative divided by negative will still be positive. So those two will always cancel each other out regardless, so they're not required in our sign test. For the rest of them, I'm going to plug it into the factored form to determine where I'm positive and negative. So, plugging in negative 3. Negative 3 minus 1 is negative. Negative 3 plus 2, also negative. Negative 3 plus 1, also negative. A negative times negative is a positive. Divided by a negative means the whole thing is negative. Plugging in negative 3 halves. Negative 3 halves minus 1. Negative. Negative 3 halves plus 2 is actually positive because it's negative 1.5 plus 2. Divided by negative 3 halves plus 1, still negative. Negative times positive is negative. Divided by negative is positive. Plugging in 0. 0 minus 1, negative. 0 plus 2, positive. 0 plus 1, positive. Negative times positive divided by positive is a negative. Lastly, plugging into 2 minus 1, positive, 2 plus 2, positive, 2 plus 1, positive. The whole thing is positive. Okay, so we have domain restrictions at negative 4 and negative 1. So we know that we are, so our zeros, as we said, are where x equals 1 and x equals negative 2. We are undefined or indeterminate at x equals negative 4 and x equals negative 1. But for where we're positive and negative, that comes from the chart. We are positive between negative 2 and negative 1. And also from anywhere from 1 on. So we'll put a union and 1 to infinity. And we are negative at the other two intervals, which is from negative infinity up until negative 2, and between negative 1 and 1. And I will leave the second one for you to do. It's good practice for factoring and using these techniques, but this is all that we will do for the Algebra Review Part 2.